Okay, thanks, Ali. I think that looks a little bit like me, maybe a bit younger and a bit less grey. So my name's Nick Hodgson. I'm Head of Particle Engineering for EUROAPI. So we are a contract development and manufacturing organisation. Main focus is actually on drug substance, but we also have quite a lot of capabilities in particle engineering. So Ali and I have had a few discussions, and we saw there was some synergy there in terms of the digital scale-up versus the digital screening approach. So I'm going to talk a little bit about spray drying in particular, and some things we're doing around really trying to be efficient with scale-up, but touching on some of the challenges that Ali mentioned before around particularly API availability, the cost, and how we can accelerate that process and get more confidence in the scale-up, going into a more GMP manufacturing environment for this technology. So I'll talk a little bit about, why spray drying. Ali's touched on that already, so maybe won't spend too much time there. We'll try and demonstrate how we do the scale-up, so what some of the advantages are, some examples of how we do the modelling, a couple of case studies, and then just a summary. So again, some of this has been talked about. I'm not a formulation scientist, I'm a chemical engineer, so I do educated guesswork for a living, so I won't explain the finer details of this classification system. But in essence, we know the drugs have solubility issues. Spray drying is one technology we can use to address that. There are several others, depending on what the solubility challenges are, but we'll focus in this case on the amorphous dispersion approach. Use of polymers to stabilize the drug in an amorphous state. There are many different polymers you can use, depending on the drug, different solvent systems. We're generally talking about organic solvent drying as well, so which adds another level of jeopardy, should we say, to the to the enterprise. So a typical spray dryer process flow, these can be at various scales, which I'll show in a minute, but typically you have the drying chamber, some way to atomize the feed to turn it into droplets of a size that you're targeting, because this has a direct impact on the particle size at the end of the process. We usually use a cyclone to separate the product from the gas flow. There's usually a filter to either to collect fines or product, depending on the particle size targets. And in most cases, we have a recirculating system, so it's what we call closed loop. We're usually using nitrogen as the drying gas, either electrical or steam heating, or maybe a combination of both, with a system of fans to keep a set flow rate going through the system, which is important for the product recovery and the drying process generally. There are different systems to atomize. You can use high pressure, you can use what we call two fluid nozzles. Again, depends on what the target is for the particle size distribution. There are different advantages of different approaches, depending on what it is you're trying to achieve. There's a bit more animation on there. So in terms of scale, you can go everywhere from the bench top, so a small unit sits in the lab. We then go through some larger units which get into the pilot scale, and then ultimately production scale, which is generally classified as PSD2. It's kind of my first industrial spray dryer, up to maybe PSD4. You can go bigger, but for pharma applications, you usually stay at the slightly smaller end, because usually the volumes are not enormous. You can go extremely large with spray drying, which we'll show in a minute, but not normal to see that within pharma. When you're scaling between these units, there are different things that are going to be different between each scale. So your feed system, the size of droplets that you can create, purely based on the scale at which you're operating, where those nozzles are located, how the drying gas is flowing around the system. Big thing is the dimension of the chamber itself, how well insulated it is, what the thermodynamics, how that behaves, loss of temperature from the system, how the exhaust gases, how the ductwork is configured. Lots of things are going to affect essentially how the drying process performs. And then these can impact a lot of different elements. So the trajectory of your droplets, that can have an impact on your yield, what the evaporation rate is like, drying time, flight time, the amount of solvent in the drying gas, So you can imagine if you've got a recirculating system with a condenser, how well that's performing has an impact on capacity of the system, the drying rate, what the final particle morphology might look like. So there's a lot of different things that are going to be impacted by the different scale and the different configurations. So our target is to try and have reliable scale up. So, it's going to do essentially what we expect. And we need that data. We have data on the dryer themselves, any data from previous scales that the system has been run at. It's all helpful in terms of trying to build that model and try and get it as accurate as possible. And then the more batches we run, we can feed information back into that model to improve it. But as Ali's mentioned as well, there's always constraints, time, API availability being the two main ones. So when we start a project, we do a technology transfer, we'll look at a gap analysis, what are the key differences between what's already been done and what we're looking to do. Do those differences matter? How much attention do we need to pay? We'll then get into the process modeling, generally on thermodynamics and kinetics. We might do some laboratory experiments as well in parallel, and then we'll basically try and prove that with what we call a technical batch before we then go into the final manufacturing protocol. But the idea is always to try and do this with the minimum amount of API as a main driver. And you can see some of the scales there from SD1 up to the biggest one we have on site, which is a TFD 250. You can see the difference in scale there from around 2 meters up to 22 meters in height, and maybe around 30 centimeters diameter up to about 6 meters. So we've mentioned material conservation is absolutely key. It's usually a high cost, particularly in the earlier phases of clinical trials, but also can be very limited in terms of the quantity that's available at any one time. And sometimes the manufacturing schedule from the API supplier is perhaps not optimal. So you have to do as much as you can with what you have. And we're trying to maximize the value. So, there are options outside of the digital space. So, we can look at things like excipient only or placebo batches. That can be useful, but it depends on the formulation as to how much you can learn from that. You can look at smaller batch sizes or shorter runs. The spray dryer itself can be quite flexible, but if you have secondary drying involved, that can be less flexible depending on the size of that unit. We can look at redissolving after we've spray dried. We've done that a few times. It's not the nicest thing to do. After the spray drying, the powder can be quite difficult to handle in terms of redissolution. And there's always a question mark over potential degradation, the amount of reprocessing the spray dry dispersion will tolerate. And we can also look at DOE, so design of experiments, so we can try and maximize the information we gain from the minimum number of experiments. Spray drying being a continuous process is quite good for this because you can alter the conditions on the same run and adapt it, so you can take samples as you change the conditions, so you don't have to run a whole batch at one set of conditions and then do another one. You can alter it on the fly, so to speak. I won't go through all this in detail, but there's a few different things that we use. So one thing is the particle sizing. So we use a model there to look at the droplet formation from the nozzle. This depends on the rheology of the solution. So it depends on our solvent system, what polymer we're using, the concentration. So we can try and predict what droplet size we'll get from the nozzle, and then how that will dry and what a final particle size will be. So usually there's a target there that you're trying to hit. There's the drying conditions itself. So there's different factors we look at here in terms of the conditions inside the dryer, what's happening with the condenser, the thermodynamics, to really try and point at what conditions should we start with, what design space should we explore, and what is the best starting point for the run. We can also model the secondary drying, so this is usually important in terms of cycle time. It can be the longest piece of the process. We've seen products go from, some might be 12 hours, 24 hours. I think we've had other products take nearly a week, to dry. So you spent 1 day spray drying and then a week in the secondary dryer. So this is important as well, and it is impacted by the formulation. You know, how difficult is it to remove those last bits of organic solvent down to the acceptable levels? So that can be a key point in terms of, you know, your later production. If that is a really long, extended period, that's really going to impact your, you know, your capacity in your system. So in terms of thermodynamics, this is a typical plot, you know, that we would see, and we choose an operating point within that design space. You know, things we're looking at here is inlet and outlet temperature. Outlet temperature tends to end up being the quality critical parameter. Inlet temperatures can be more flexible, but there can be limits, upper limits on that, depending on the product and the formulation. Relative saturation is important, and, you know, what is our minimum throughput rate? So typically what we would do is define what the design space is and then choose an operating point to start with for that particular process. In terms of some examples on kinetics, you know, particle size, we might want to look at the drying rate, the efficiency of the cyclone. Customer usually has particle size targets for various reasons. So we can usually target, you know, pretty much where they want to be. The model is quite efficient these days. So we can say what is our droplet size and what particle size do we end up with by the time the system is dried fully. Nozzle selection obviously is key to that. How do we achieve it? What feed rates do we need to achieve it? What spray angles? You know, does it give us a good pressure if we're using high pressure systems? So there's all these sort of dependent, independent variables that we're playing around with to hit the right conditions in the drying system. DOE, just a little bit in terms of how it applies in spray drying. So once we've run the model, we've maybe come up with a set of conditions or maybe a range that we want to explore. You know, how do we minimise the amount of testing that we have to do? So DOE is very helpful for that. You know, we can vary multiple variables and use multivariate analysis. So it really minimises the number of experiments we have to do. And this is really key, especially when you're going up to the PSD2 or above. You know, you're using larger amounts of material. So, you know, the client is very keen that you maximise the use of that and you generate the most data that you can while you're doing these batches. We've had occasions where, you know, a typical batch size on a PSD2 might be 50 kilos. We've had clients ask for batch size of around 3 kilos in this system. Now, that may seem a bit strange in terms of why would you want to use that scale for such a small quantity. Sometimes it's driven by, you know, they need to prove the process at scale for, you know, investor stage gates and things like that. It's important to have the data to show the process is scalable, but there's a minimum of API available for this type of testing. So we have accommodated that. It's not ideal, but it can be done. But this helps, you know, when you've got a really small amount of material like that, you know, that might give you 2 to 3 hours runtime. You can actually maximise the data that you get, you know, from that run by using this approach. So just some case studies. So kind of two ends of the spectrum really. So this one was from an extremely large scale process that was needed, but ironically there was still a major issue with availability of the product to actually do the testing and doing the scale up. So this wasn't because of, well, it was because of availability, but also demand. The client couldn't supply us with, you know, reasonable quantities of material for this scale because of, you know, the demand that was in the market at that time. So we had to use a very small quantity. We were scaling this up around 10 times, and they wanted it very fast. So we had to go, we were changing parameters as well. We went from a closed loop to an open loop configuration, and we were running in excess of 300 kilos an hour in this case. And we had to do that solely based on the modelling because the previous scale was nowhere near this kind of level. So we ran the models. We did two sort of, well, I'd say, truncated DOEs with very limited material. And we went to manufacturing, you know, I think it was well over 100 tons of material within 12 months of that initial inquiry. And most of that time was actually, you know, getting this material available to do any of the testing. But I honestly believe that this particular project, would not have been possible without the simulation. Because I don't think any of us, us or the client, would have had enough confidence to actually then put the product into that scale of dryer, with the financials that were at stake on the project. And then at the other end, this is on a PSD2. So I mentioned this a little bit, extremely limited API supply, less than 5 kilos available. We're scaling up around 6 times in this case from it wasn't actually a PSD1, it was actually a lab scale unit. And it was an API only formulation, which is quite unusual. So there was no excipient in this case, but it was very temperature sensitive and could degrade quite readily if we essentially overcooked it. So we went straight into PSD2 based on the process modelling from the lab data. That's not ideally how we like to do it. We like to have a little bit more robust data before we go into the PSD2, but this was a particular scenario and the client was very keen to prove it at scale. And actually, yeah, we were really pleased with the performance. The control was really good. Really stripped down the approach to scale up and still got a good result. And we did a subsequent GMP batch, which was successful. I think we almost made a rod for our own back with the client there because it worked almost too well, and they expected a similar level of performance on all the subsequent batches. But again, without the mathematical modelling, without that confidence that's generated from those numbers, I think that would have been something we'd have had to do in a slower way. With probably an intermediate scale-up step in the middle. So, as a summary, we use spray drying as a key technology to enhance the bioavailability of a drug substance. There are lots of things that can affect the scale-up and the critical quality parameters. So, while in essence it's quite a simple process, the devil's in the detail. Lots of different things can affect how well it performs. And the simulation can really help us evaluate those with a good degree of certainty before we go into the industrial environment. I think we've shown on several occasions now on lots of different products that the mathematical modelling really does accelerate the chance of getting that right first time. And then the DOE can help sort of augment that. So once you've got a set of conditions that works, we can explore the operating space and give the client a little bit more wiggle room, if you like, in the operating conditions on the process. So we can explore that in an efficient way. And we've proven this approach in quite some quite different scales across the different dryers, from the lab scale into the PSD2, and then up to the very large industrial unit, 20 plus meters in height. And the models are bespoke to each dryer, but they all have common elements. And as I say, what we tend to do is when we run a batch and we get some good data, we'll kind of feed that back into the model. So, okay, how accurately did it predict it? Can we improve the model based on the feedback loop, essentially? And I think this ties in with a general approach to try to accelerate or expedite the whole process in terms of how quickly can you get to the stages, get into clinical trials, manufactured, or produce material for tox studies, more rapidly. And this is really important, I think, for a lot of clients that we see, perhaps smaller or virtual pharma that come along and want, to really maximise the value of what they get from their campaigns. And I think this tool or set of tools really helps us achieve that. I'll go through the disclaimer and then thank you very much. Any questions?
Thank you very much.
Sorry, but you've confused me. It's not difficult. I'm a bit confused about the scaling.
Yeah.
I'm going to have to assume that given spray drying is a continuous process, is it the other unit operations involved that necessitate the scale up? Also, why don't you just run the smaller scale PS2 for longer?
Yeah, so this can be done. So yeah, sometimes the rate limiting step might be the dissolution. Sometimes the dissolution step can be quite problematic, or it could be the secondary drying. I think the scale that you would run at for the spray dryer itself depends on, I think, often what the client's projections are for the ultimate volumes commercially. So often you could scale, what we call scale out, so you could just number up, and indeed that is an option. It can get congested because you might not have enough assets, to run enough material through. Sometimes the secondary drying is not required, so you take away that constraint. But yeah, what we do with the client initially is look at what are their projections, what are their ultimate volumes going to look like. You can always guarantee it's going to be wrong, but get a sense of that. And then what we would do is then choose what we felt would be the appropriate scale to run or to scale up to on the spray dryer, so that definitely isn't the bottleneck, for them, down the line. And typically, a PSD2, I mean, so you might get a smaller PSD1 in a GMP environment, but PSD2 is quite a nice scale because it gives, I think, enough capacity for the client to feel happy they've got enough headroom. And, like you say, you can augment the capacity with other unit operations there. The other thing is a lot of clients don't want to be taking up more than a certain percentage of a capacity on an asset. So unless they own it and it's dedicated, most clients get uncomfortable if they're taking up more than, say, 30% of the capacity on a unit. So they'd rather scale up or have an additional asset online. So it depends on their drivers. Others will look to co-invest, and perhaps have a dedicated asset if it makes sense for them.
Hi, it's Steve Facer from Adair Pharma Solutions. If you make variable changes in a continuous process, how easy is it to collect the discrete dispersions that you've then changed and want to analyse? Yeah,
it's a good question. I think what we tend to do is we'll alter one or more parameters, and then we usually allow, say, a few minutes for it to stabilise and essentially reach steady state again. It's usually quite quick, and the actual residence time in the system is probably measured in seconds rather than minutes. But you maybe give it a little bit of time, just to make sure you're definitely collecting, the new conditions and not the previous conditions. So usually it's quite straightforward. You can either collect it direct from the cyclone, just in putting a different catch pot on the bottom. So there's no issue with closing the cyclone for a few seconds while you change the container, and then just collect under the new set of conditions, and then either go back to the main collection pot or change your conditions again and go to a new sample. So it's relatively straightforward. I think it's just allowing a little bit of leeway, to make sure, yes. Exactly, yeah. So there will be a time when it's adapting, and you'll get a little bit of a mixture. But yeah, normally it's quite fast. So you can do quite a lot of experiments in a short time if you're smart with the changeovers. Yeah.
Thanks. Yeah, just about you talk about the size of particle and like this, and did the impact of the initial formulation or solution that you spray dry don't have any impact at all in the...
So yes, it can, mainly in terms of when we're spray drying from a solution. The solution properties will have an impact on how the droplets form from the nozzle that you select, and the type of nozzle. So you could use high pressure, you could use, as I say, too fluid, where you're using a gas to then atomize the solution. So yeah, absolutely. If it's more viscous, for example, it's going to behave differently, through the nozzle. You'll have different back pressure in the system. So all this needs to be taken into account when you select the nozzle. The other complicating factor is sometimes you might spray dry a suspension or a slurry. That's then more dictated by, how has that slurry been prepared? Has it been wet milled or something like that? So what are the particle sizes of the actual suspended solids? Versus a solution, it's actually a bit more straightforward because it follows the rules a bit more. But yes, absolutely, has a big impact. Yeah.
Thanks. Very, very, very interesting. So, I guess that this a lot of this is made in the UK, in Haverhill.
Yes, correct. Yeah.
What are the scales of this operations, you're really in the development part of the company, I guess?
Yeah, so we can do, I mean, everything from the bench up to very large scale. So, you know, we have a number of, you know, Buki units, benchtop units that are really used for proof of concept. So if someone wants to prove if something's even feasible to spray dry, we tend to use those as an initial look. We have a Procept SD1, which is a smaller scale, or let's say large lab scale unit. It's also GMP capable. So this might be a batch size of maybe 2 to 5 kilos. Can be useful to support scale-up work if you wanted to do some more experiments at a smaller scale and then scale them up again, into the PSD2. PSD2 is I guess, the most popular one in terms of scale. So that is it's useful for clinical trial support, tox materials, could be launch volumes, could be registration runs, things like that. We have a PSD4, which is currently not organic solvent capable. It's aqueous only. So that is, let's say, 5 to 6 times bigger than a PSD2. And then the very large scale ones we have, which again are aqueous only, tend not to use solvent at the very large scales. So this would be, say, 10 times bigger than a PSD4. So you're talking about evaporation rates of 1,000 to 1,500 litres an hour of water. So depending on the feed concentration, you know, you could go from, say, 30 to even 300 kilos an hour through a system that size. So, you know, we do everything from a few grams all the way up to, you know, several hundreds of metric tons per annum.
How many of the batches or test batches you do?
So it depends on the schedule. So I think if we're looking at the PSD2 operation, you know, you might look at in a sort of development clinical environment, you know, you might be looking at, say, 25 to 30 batches in a typical year. So usually a client campaign might consist of, say, 3 to 4 runs in terms of, usually you'll do the confirmation batch or the technical batch. You then might do 2 or 3 GMP batches, or they might want material for toxicology studies. So it's a bit variable, but, you know, you might have, say, 6 or 7 different clients through there in a year, with perhaps a mixture of a different number of batches. You know, if you had a point where a client wanted a more, you know, you could sort of turn the handle and they just wanted a certain amount of batches over a 3-month period, for example, you could really push your productivity up because you're doing the same, you know, the same product kind of day in, day out for several weeks or months. So, I mean, in terms of output, a PSD2 with supporting infrastructure might do anywhere between sort of 3 to 7 metric tons a year, depending on how it's configured and, you know, the batch configurations and the concentration of the feed and lots of different elements, but around that sort of region.
One more question before we go to the next speaker.
So do you guys have the capability, once you've produced the dispersion, to do subsequent formulation work, or do you normally just leave that with the client?
So at the moment that's with the client to, you know, to take that on. So as I mentioned, EUROAPI is very much a kind of drug substance background, so a lot of synthesis capability for drug substance. We're on the boundary, if you like, you know, with the spray drying, turning that into the drug product intermediate. It is something we've discussed in terms of could we offer that perhaps at the small scale, particularly for the clinical trials. You know, a lot of clients do ask for that, just as almost like a one-stop shop. But at the moment, yeah, we would give them that dispersion and they take that on, you know, to whoever they're using for their final formulation. Yeah.
Okay, thank you very much. Very
Thank you.
interesting. Okay.